imagine if there were pizza trees, bar bushes, and soda roots.
Bushes that grew bars like candy bars and lard bars and stuff. And so what's a soda root?
It's like a soda with like roots going out of the thing.
Oh, so it's just like it's just the sodas that grow up out of the ground.
Yeah.
The world would be better that way, wouldn't it? I agree. Thanks, man. That was awesome. All right, so instead of having like pizza trees, we're gonna have heats of formation and heats of reaction today, guys. So hold on tight, cause thermodynamics, here it comes, man. If we could thermodynamically engineer a pizza tree, I think that we would make millions. I think so. Like, that'd be awesome. All right, this is our final installment here of thermodynamics. And this, see, like what we looked at before now, like all this stuff that was higher up on everything, was all about measuring the chemical reaction that is happening in front of us, right? With like calorimetry and like understand like blah, 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 exothermic, endothermic, all that good stuff. But what we really like to do is be able to make predictions. You know what I mean? Because like we want to know what's going to happen beforehand so that we can count on like things going the way we want, right? So we can count on something being exothermic enough to like give off enough heat or to like absorb enough heat. Like we want to know beforehand. And again, one of the biggest points of science is to make predictions that are like true. So what we're going to talk about today are the heat of formations and the heat of reactions and how we can come up with how we can predict the heat of a reaction, right? And so we can't do this like just on our own. What we're going to use is like we're going to see far by standing on the shoulders of giants, and we're going to like use a lot of data that's been gathered over like a whole lot of time, and we're going to like look a lot of stuff up. So one of the things that I have over here, I closed my page, stupid. In the book, like if it was for real, we'd use like the physician's desk reference or something like that. But since we're not using the physician's desk reference, we're using Appendix 3. In your handy dandy thingamajig, see Appendix 3. It's got all your heats of formation for all kinds of elements and compounds. Well, elements you don't really need to. So there it is. You can look up a lot of this stuff. You can just look it up, and then we're gonna go through today how we can predict the delta H for a reaction that we don't really know, like if it's a new and unique reaction, based on measurements and experiments that we've done for the past who knows how many centuries. All right, so here we go. There is no way to measure the absolute value of enthalpy of a substance. In other words, we cannot pick up a piece of firewood and be like, I know exactly how much energy there is in here. The only thing we can do is measure the change as it goes from cellulose to carbon dioxide and water vapor. But even then, there's still energy inside the carbon dioxide and water vapor. So it's all, there is no energyometer. There's nothing that directly measures the energy. So we have to go a little bit indirect for this, okay? So what we've done is we have basically a scale-ish that we just were like, let's pick a starting point, right? And so what we started point was this thing. It's called the standard enthalpy of formation. Yeah, so the standard enthalpy of formation, here's how this thing works, man. It's basically the amount of energy it takes to like, make stuff. I don't know how else to say it. God, this is the most annoying thing in the world, guys. Sorry. Yeah, let's go like this. Oh man, this is like gonna make my head pop. So this is our reference point. I want you to look at this thing right here, right? And this is delta H 0F of formation. In other words, this is like standard. This is like what we're standardizing, right? And so what is this thing? What does this symbol mean? It's basically the amount of energy it takes to create something, right? And it is from when 1 mole of a compound is formed. Now this is really important. From the elements. It has to be formed from the elements. Okay? Because what we say, like, again, this is like an arbitrary method that we did this. but it's standardized, so we do it the same to everything. So that's kind of how this works. As you said, the elements have a delta H of formation, like a heat of formation of 0, because that's sort of how they start, right? There's a supernova out in space, and kablooey, all the elements are formed, and that's kind of where we start. So we're calling that 0. So if those elements get together and energy is released, the delta H of formation is going to be negative. If it's an endothermic, it could be positive, indicating that it's like less stable than just the elements. You know, that kind of thing. You guys are like really smart. You guys will figure this out. So times, like I just said, the elements start out as 0. They start out as 0 so that we have some kind of like starting point. I mean, that's really what we need, and that's why this is considered arbitrary, because why are the elements 0? Just because we said so, right? There's no like natural phenomenon like dictating this. It's just us saying that that's how it is. So what does that mean for us? That the heat of formation of O2, because this is oxygen in its natural state, like that's how we naturally find oxygen, we call this 0, because that's how, it's just how it is, like under normal conditions. However, oxygen also naturally occurs like this in the form of ozone. However, because that is not the overwhelming natural state of oxygen under normal conditions, we say that there's a heat of formation of 142 kilojoules per mole, indicating that we have to put in 142 kilojoules of energy to go from O2 to O3. And what that tells us is that O3, this compound has a lot more stored potential energy and is therefore a lot less stable than our elemental oxygen. You guys picking up what I'm putting down there? I certainly hope so. Same thing over here. Graphite, and also this is not for nothing, but graphite is what we have decided to use as like the standard elemental form of carbon. Why? It's pretty stable. I think it might be one of the most stable, but still structured. So we chose graphite. And so to go from graphite to diamond, if you look, it only takes 1.9 kilojoules per mole. So, you know, we had to put energy into it. It requires a little more energy. There's a little more potential energy in a diamond than there is graphite, indicating that diamond is actually a little bit less stable than graphite. However, not a whole lot more, especially in comparison to this. I mean, look at that. That ozone is way less stable than oxygen. And we would think that because the delta H of formation is so large, and it turns out really true. So the standard enthalpy of reaction is the enthalpy of reaction at 1 atmosphere. This is really what we've been calling delta H, but we're going to be a little more specific by calling it the delta H of reaction. Okay, and we're doing that because now we're going to look at a whole bunch of different delta H's, like what happens when we look at a chemical reaction as heat of formation of the elements, heat of the reaction. There's going to be a lot of delta H's, so we're just going to try to be a little bit more specific with our language here. And now look, I'm going to do some doodling here, and then like the notes will like do my doodling for me. But look, what I want us to do is I want to look at this, right? These I'm going to call R for reactants, and then let's see here, these over here I'm going to call P for products, right? So for energy, right? Like if we're going to be looking at energy, which is kind of what we're doing, the change in energy is going to be equal to you know, some days are good, some days are bad, and some days Stu has to learn how to use technology. So what this is going to be, this is energy final minus energy initial, just like anything else, right? So what is this? What is my final energy, and what is my initial energy? Well, my final energy, as it turns out, is the energy of my I did that wrong. Final is over here, so that's going to be the energy of my products minus, you see where I'm going here, right? minus the energy of my reactants. Right? So this is going to be the sum of the energy of my products. This is going to be the sum of the energy of my reactants. That's really as complicated as this whole equation is going to get is right here. The change in energy is going to be equal to the energy of the products minus the energy of the reactants. You guys got that locked in there? Okay. Now, I want you to keep in mind, it is just this simple. Now, the symbols are going to get a little bit weird here for a minute, and it's just because, like, we're trying to express things using math, and, like, math starts getting into some, like, weird symbols, you know what I mean? But, don't worry, we're going to be okay here. I'm going to erase. I'm going to start drawing in yellow. Are you ready, guys? Boom. Here's our thing. So, the heat of reaction, right? This is our energy, right? So that's our the change in energy. The delta H of reaction, or the heat of reaction, is equal to the heat of formation of our the moles, like the number of moles of our substance, heat of formation of our substance C, plus the number of moles of our heat of formation of our substance D, minus, guys, that's the sum of the energies of our final minus our initial energies. Now this is describing how we calculate the final energy. This is describing how we calculate the initial energy, and it works like this. If we have 3 of A's and 2 of B's and 1 of C's and, I don't know, let's say 4 of Lee's, right? So what we're going to do is we go look up the delta H of formation in our appendix in our textbook, and it says that for every 1 mole it takes, I don't know, 5 kilojoules for pretend. So if it took 5 kilojoules for every mole and I have 1 of these, it'll be 1 times 5 plus. All right, so this is for this substance. So there are 4 moles, and let's say we looked up this substance D, and it said it's going to take 2 kilojoules per mole. It's going to be times 2 kilojoules per mole. Now, it's going to be a little messier than that, of course, because, you know, nature doesn't use clean numbers. And same thing over here. The number of moles times the heat of formation, number of moles times the heat of formation. And again, these heats of formations, all of them, these are what we're going to be looking up in the appendix. This is not something to memorize. You guys got that? Please remember that you are not memorizing this. All we have to do here is look it up, okay? So here's what that's going to look like when we get all fancy. So the heat of reaction is the sum of the number of moles of the heat of reaction of the products minus the sum of the moles of heat of formation of the reactants. It's exactly like what we were saying. It's just got some weird symbols there. But does that make sense? It's just final minus initial. Like so if you know the heats of formation for all 4 of these substances, it's really awesome. You just bam, you just look it up. And how do we know that? How do we know the heats of formation? Because we've done it 75 million times over the past 200 years, and it's been the same every single time. That's how. Do you see how much she loves me? Do you guys see how much she loves me? What did you bring me? What is this? Is that grilled cheese with some? It's a grilled peanut butter and jelly. Guys, we're gonna have to time. You have to time. We're gonna have to time out. Seriously, guys, grilled peanut butter and jelly. Are you kidding me? How can you? I mean, I know you might think it's dude. Just okay. Try it. Okay. Mm. Mm. Seriously. Oh my god. It's so good, guys. I don't even know what we're talking about here. Oh yeah! Sorry. Heat of reaction. Oh man, that was so good. Whew. Hess's law basically says everything that we said right here. Man. So, this means delta H is a state function. Doesn't matter how many, like, different degrees or states or, like, steps or anything we have to do. It is a state function. This is really nice because it holds true. Remember? Do you remember way back in the day when we did, like, potential energy diagrams and it looked like this? We had to go from reactants to products, and over here we had the activated complex, right? Remember that? Well, Hess's law says that, yeah, you probably had some intermediate, like, steps, but really in the end, when it comes to energy, the only thing that matters is the difference between final and initial, and that is it. So that's kind of what Hess's law is saying. Makes this really... No, go ahead. Makes it really convenient for us because there's nothing else for us to do. Just beginning and end, and that's it. We don't have to look at the path that it takes. Thank God, because this is, like, messy enough. Right? Yeah. Oh, yeah. State function. Doesn't matter. So here is what this is going to look like actually in action. That's me getting sprayed. Wait. That's me getting sprayed in the face by a bombardier beetle. It would be really bad. It would really suck. So here's the deal. This is kind of how this works. We had this new and unique chemical reaction. So good, guys. Seriously, grilled peanut butter and jelly. You have no idea. It's a comfort food, man. So here's the thing. We have this reaction here. We've got C6H4OH2, this weird looking like diol mixed in with hydrogen peroxide, and it spits out, I don't even know what compound that is, an H2O. And what is the delta H? So first thing, let me see if I can connect a video about the bombardier beetles. These things are amazing. They like squirt out of their butt like toxic boiling juice of like acid, and actually it's not acid. I think it might be a little caustic. There might be some causticness in there, but really what it is, it's hot. It's like boiling hot water. And you're like, man, how does this beetle shoot boiling hot water out of its butt? It was actually a mystery for a very long time until they dialed down the chemical reaction. Next thing was like, how? Like physically. Anyway, because we're the chemists, we're only going to worry about the chemistry here. And here's how this do. This is our new... Oh. This is our new reaction, right? So this is what we got to take a look at. So if it's new and we don't know anything about it, what we might be able to know is go into the physician's desk reference and see if we know how much energy it takes to create this chemical, how much energy it takes to create that compound, and this one, and that one. And then what we're going to do is we're going to mix things up and we're going to add things together. Does that make sense to you guys? Oh, maybe not, but just follow along and everything will start to make sense, you know, or not. Like, it's entirely possible that this may never make sense because that would make you just like everybody else in the whole wide world. All right, let's go with that one. So, whoa, my face out the way. So, where? I'll go over here. No, I'll go down here. I'll get sprayed in the butt. It's gross. Butt spray. Anyway, so here's how this works. We can go to the physician's desk reference, just like a book or in the back of your textbook, and we know that this reaction, or that this thing, this compound, it degrades into this one, and hydrogen. Oh. And it's going to absorb 177 kilojoules per mole. How do we know? Because we have probably done this 75 million times, and we can just look it up in a book. We also know that that H2O2, hydrogen peroxide, it's going to degrade into water and oxygen, and it's going to be -9, so it's going to be exothermic. How do we know this? Because we've done it about 1 million times. And same thing with this one, the reaction between hydrogen and oxygen. We know that this thing like is exothermic, and we know because we've done this like 1,000,000 times. Does that make sense? So how did I know to choose these equations? Well, I know that what I have on the left on my reaction, on my reactant side, is this little diol. So that's why I put this diol here. Does that make sense? I've also got H2O2, hydrogen peroxide. That's why I chose H2O2. Does that make sense to you guys? So also, another reason I chose this one is because over here I have hydrogen gas, And hydrogen gas is not a part of this equation. So I need to get rid of hydrogen gas. And just like any other equation, what I have on, if I have it on the left and the right, it just cancels out. Does that make sense? So that's why I'm choosing this reaction. It has hydrogen over here and water over here. And this one I chose specifically because I have water in my original reaction, like the one that I'm trying to understand here. Does that make sense? So basically, what we do is we go look up a bunch of equations. Now, a lot of this is going to already be done for you. Like, you don't, this is like, you don't need to, it's like pages and pages and like, it's a volume of a text to try to go through these. Most of these are going to be given to you. But the concept here is that what we can do is we're going to take these and we're going to mash them up and smoosh them all together into one giant equation. But before I do that, remember, anything on the left and on the right gets canceled out. Does that make sense? And what I want to be left with is my diol and hydrogen peroxide, because these are my reactants for my weird, like, bombardier butt boiling spray. And I want to be left with this crazy molecule and some water. Does that make sense? Let's check it out. So over here in the reactant C6H4OH2, I don't see it anywhere on the product side, so we're going to leave it. Here I have H2O2 hydrogen peroxide. I don't see hydrogen peroxide anywhere over here. Oh, okay. Here I have H2. I'm going to change up my color so we can really emphasize this one. I have hydrogen gas on the left, one of them. I have hydrogen gas on the right. They will cancel out. Right? Because if I have it on the left and I have it on the right, they cancel out. And here I have 1/2 of an oxygen. No other oxygens here to add to it. No oxygens, water. Oh, here we go. So 1/2 oxygen gas on the left, 1/2 oxygen gas on the right. That is beautiful. So once I mash these up, the only thing left on my reactant side is this weird diol and my hydrogen peroxide, which is exactly what I have here. And over here on the product side, I have this weird compound, which is right here. And I have 2 waters. And it turns out I've got 2 waters right there. Bam. So that's going to give me my complete new, novel, unique, and unknown reaction. To find the delta H's, I'm going to take 177 minus 94.6 minus 286. And whatever I have left, that's what I have left. So the first one that we did was like final minus initial, and that's if we could look up and we knew everything, like it was just heat to formation and things that we knew. But for this one, because it's a new and novel equation, right? This is a new thing that we're trying to study. We had to go and like look at equations that we already knew a lot about. Does that make sense? Great. I hope that makes sense. Yeah, so look, that's exactly what we did. We took 177, we took minus 946, 286, and we basically added them all together, and my delta H for this reaction is this right here. Highly exothermic. Very exothermic. So exothermic that the stuff coming out of this right here is actually going to be boiling hot enough to kill little insects and stuff. Not hot enough to kill like you or me, but enough to to hurt us. Like we'll probably be like, dang, and not want to like mess with them. How's that happen? Man, I don't know. Nature's a weird beard, man. Weirdy beardy for nature. If you need that, there it is for you. Here is another example of what it is and how like the what I want you to see here is like how the equations are going to be like right there for you, so you don't necessarily need to go searching for the equations. So I don't want you guys to freak out about that. So let's read. Calculate the standard enthalpy of formation of acetylene. So this stuff, I want to find that. That's the stuff I'm looking for. So enthalpy of formation should not be doing it with that. I should be doing it with this. That's bad enough handwriting. Okay, the delta... Whatever. The equation for each step and corresponding enthalpy of changes are that. All right. So, where can I put my face that it's not in the way? There's really no place for my face to go today, guys. Maybe I'll put it right here, but it needs to right there. I'm just going to leave it. How about I just leave it way up here in the corner? I'll cover up that mess. All right. So here are the three equations that we're given. Graphite plus oxygen yields carbon dioxide. The heat of reaction is exothermic. We have hydrogen, and half of an oxygen gives H2O. It gives that. And two acetylenes need 5 oxygens in it. Okay, sweet. So let's see what we need. For our final thing, we're going to need graphite on the left, hydrogen on the left, and we're going to need acetylene on the right. You see this here? We need acetylene on the right. The problem is we are given acetylene on the left. Oh, and there's 2 acetylenes. First things first. Like we talked about before, if acetylene plus oxygen yields carbon dioxide and water and is exothermic of that amount, we can also say, for carbon dioxide plus 2 waters will yield 2 acetylenes and 5 O2s. And the delta H is going to be positive 2598.8 kilojoules per mole. It's basically just going to be opposite. You guys understand what I'm saying? Do you guys see what I did there? I took this equation and I basically flipped it. And the reason I did that is because I need the acetylene, the ethylene, depending on how fancy you want to be, I need it to be on the right. Whoa. Yeah, let me fix this. Give time out. There, that's what I wrote in the first place. I don't know if you caught that, but that's what I had. I flipped it. So instead of ethylene, acetylene plus oxygen yields carbon dioxide and water. Carbon dioxide and water yields acetylene and oxygen. You just flip it, right? And that's what I do with my delta H there. So let's check stuff out here. I'm going to need 2 graphites. So, because I've got, and I've got 2 here. So what am I going to do here? I need 2 graphites. And I only want 1 of these. Okay. I see what's going on here. So if I want two graphites, I'm just going to take this whole, man, I hate that when it does that. I'm going to take this whole thing, I'm going to multiply it by 2. Does that make sense? And that'll give me 2 graphites, 2 O2s, 2 carbon dioxides, and it'll give me 2 times 393.5. I need 1 hydrogen. Yep, that's what I got. 1 hydrogen right here. And over here, I need 1 acetylene. But here, unfortunately, I have 2. So what I'm going to do is I'm going to multiply everything here by 1/2. So that'll give me 2 carbon dioxides. It'll give me 1 H2O. Right? It'll give me 1 acetylene. It'll give me 2.5 O2s, and it'll be half of this. Does that make sense? So let's go through and see what we can do. So I've got 2 graphite here. Do I have any graphite on the left? Nope. I have 2 hydrogens here. Do I have any hydrogens on the right? No, I don't. I have 1/2 oxygen of an O2 here. No. I have 2.5. So half here is going to cancel out that 5, so I'll be left with 2 O2s there. All right. Here I have 2 carbon dioxides on the left. How many? Oh, look, I have 2 carbon dioxides right here. So it looks like my carbon dioxides are going to cancel out. And here I have 1 water. Do I have water anywhere else? Nope, just 1 water. Oh, look, I have 1 water here. I have 1 water here. That's good. All right, am I done? Let me double check. Graphite. No graphites anywhere. 2 O2s. Canceled out that O2. Oh, I missed this one. Look at that. So this O2 can cancel out that O2. I missed it, but look, I just double checked everything. So it's all good. 1 hydrogen. There's no hydrogens over there. These are all canceled out. So over here I've got 2 graphites and 1 hydrogen. Okay, let's see what I have over here. That's gone. That's gone. I'm left with 1 acetylene. Oh my gosh, and nothing else. Is that it? Yeah, dude, I think that's it. That's phenomenal. So, to figure this out, it's going to be 2 of these. So it's going to be, I don't know, that's about minus 400. So let's say minus 800, minus 1100. But this is going to be positive. So you add those all up together. Nice. Done. That was easy, right? That's so easy. This stuff is so easy.
You talking to the computer?
Yeah, talking to the computer. All right.
Currently?
Yep. All right. So this one, thermite. Man, thermite is awesome, guys. Let's look at thermite. Thermite reaction involves aluminum and iron 3 oxide. Here's my equation. This reaction is highly exothermic and the liquid is formed. Man, it's just so cool. So what we're going to have to do is calculate the heat released in kilojoules per gram of aluminum when this reacts. And so oops, right there. And let's see if this is such a cool video, man. Thermite's awesome. So in Europe, this is how they weld railroad ties. Oops. This is how they weld railroad ties together out in the field, because the railroad ties have to be like all one piece, and they can't move them when they're that big. So this is what they do. So all that is making it really warm, setting this like that thing right there, which is like a form. That's all they're doing. That dude right here, this guy, he just lit the thermite reaction. And so inside that tube right now, you have aluminum, you have iron 3 oxide going. It appears to be slightly exothermic, guys. just a little bit. And oh, there you can see the liquid iron pouring out of the container. That is just the coolest thing ever, man. And there's the excess pouring out into the trays. Like, this is just so BA, dude. All right. So on the right there, those are your trays of excess molten iron. You know, just another day on the job. All right. All they do is got to remove the form, bang away the excess. And this is a specialized grinding tool to make everything nice and smooth, so when the trains go over top, if they don't, like, you know, hit a bump and fall off, because that'd ruin everybody's day. It's so cool. I miss my calling, dude. I should have been working on the railroad. No, I was wrong. That wasn't the grinder thing. Maybe that was a clamp holding it. Man, I don't know. So what he's hitting is the molten iron that came out of that thermite. I mean, you want to talk about exothermic, man. That's stupid. There's the grinder. That's all she wrote, man. Thermite. Super awesome. Not gonna lie. Alright, so here's our info, guys. Here's how we're going to solve this one. We have aluminum plus iron 3 oxide is going to yield aluminum oxide and like regular iron. We know that the delta heat of formation for this, for the iron liquid, is 12.40. So I'm hoping that these things are common and found in here. Otherwise, I'm going to have to find a whole bunch of... And I also noticed that there aren't a bunch of reactions given to me here. Like, I see nothing down there. There's nothing over there. So I'm hoping that my appendix is going to have some heats of formation for me. Let's double check. Appendix. Yeah, it's a pain in the butt, but you have to have your books. Oh, appendix. Oh, sweet. Here it is. I do have some heats of formation. Oh, sweet. I just found it. Okay, so I just found that the delta H for Al2O3. This is on page... it says A-8. It's in the way back of your book. Minus 1669.8. That's in kilojoules per mole. So that's that. I found that one. Aluminum. If it's an element, remember it's going to be 0. That's just how that is. So let's look for delta H of our iron. I'm hoping it's in here. It should be, because they didn't give us anything else to go by. B, C, D, E, F. Oh, also, in this appendix, it's all listed alphabetically. So all the elements and compounds right there alphabetically. Oh, it even says, like, Fe, like elemental iron is 0. But I'm looking for Fe2O3. Oh my gosh. Minus 822.2. That is so awesome. And oh look, I've got right here for the liquid iron is going to be 12 positive 12.40. That is awesome. So if you remember, like this was the first example. If you want to find like the heat of formation for this reaction, it's all the energies of the reactant. So I'm going to do this here. The delta H for this reaction is going to be equal to the delta H of the products minus the delta H of the reactants. And so I'm just going to blow this up a little bit. let's go with products over here. So here are my products. The heat of formation for Al2O3, my aluminum oxide, is going to be minus 1669.8. Oh, there are 2 here. Okay, so it's going to be 2 of my 12.4 zeros. See, the sum of the heat of formations for my products minus, now I'm going to do the heat of formation for my reactants. Aluminum is 0, so I'm not even going to write it. And then I've got 1 iron 3 oxide, which is minus 822.2. That's it for my reactants. So I'm gonna math this out. Be back in a sec. Okay, I got 822.8. So the delta H. Sweet, but we're not done there. So in order to fully solve this, we're going to have to come per gram, right? So it's per gram of aluminum. And in the interest of not having a video that's going to go 10,000 miles or 10,000 years, what we're going to do is we're going to convert the grams of aluminum to moles of aluminum. Does that make sense? And then we take, for the final step, we're going to take moles of aluminum, and we are going to multiply that by 822.8 kilojoules per mole. I believe I got minus there. That should be a minus. I think I forgot that. Yeah, it should be a minus. Dig. So that's going to, and this will be our final answer. Moles times kilojoules per mole. Good? Great. Enthalpy of solution, guys, I'm going to burn through this really, really fast. It's the amount of energy it takes to dissolve something, basically, because it does take energy to dissolve stuff. Sometimes energy goes in, sometimes energy goes out. Sorry, the delta H of solution is, you know, the internal energy of, or the heat of, like, where you, like, final minus initial. So this would be like crystalline salt. This would be the delta H of, or the heat energy of, like, dissolved salt. And what I want you to look at right here, this is a good one. When you dissolve table salt, it is, the delta H is a positive 4.0. What this is telling us is that this is endothermic. So think about that when you think about the salt challenge. Remember, you put a pile of salt on your arm and then you put an ice cube on it. Why does it burn you? Well, you know, science will tell you that right there. And here is kind of like the idea or the theory behind this. If you take like a salt crystal, it takes an enormous amount of energy to break these things apart, to like break these individual like ionic bonds holding all these little particles together. It takes 788 kilojoules per mole to separate these ions. Now, once you take this gaseous form of our salt, once we hydrate it, in other words, we start forming all these hydrogen bonds between the ion and the water. You dig? See, all the positives are to oxygen, all the negatives are to the hydrogen. When you do that, this makes a much more stable configuration, and it gives off a bunch of energy. But if you look at these two energies, it's not quite the same. Do you understand what I'm saying? So as you can see, it takes more energy to break them apart than you get all the way out. That makes dissolving water, right? An endothermic reaction. And remember, because it's a state function, we don't care that first you got to break them apart and then you got to hydrolyze them, or hydrate them. We don't care. The only thing we care about is, like, we care about the delta from this to that. That's that. You guys get what I'm saying? Excellent. I like most certainly hope so. Oh, review questions. Yay! Yep. Oh, look, I'm even saying evens. Man, if I have to keep telling you guys that, I don't know. But if you'll notice, I think that this might be all that we have for it. Is this like the end? Oh my goodness, guys. Is this the end? Guys, this is the end. I don't have any more slides. This is the end of the chapter. What could that possibly mean? Don't act like you're not psyched.